Okay, so we talked about DDA, annotation level, MSMS, but yeah, let's see. Okay, now the big question is, what are we going to do with it? And I want to throw already one concept out to you who have not used it before. And I think this, to me, has been really like a game changer in non-target metabolomics. And it's like very fascinated to then like work with like the people in San Diego who actually like developed this. And this is molecular networking. And if you have not heard about it, it's a relatively simple concept that has been applied already before to like some peptides, MSMS spectra. But yeah, I think like perhaps like metabolomics and especially like the search for like new metabolites and natural product research is like, I think it's particularly useful. And yeah, like the idea behind molecular networking is that we like take all this MSMS spectra from like a non-targeted experiment, and then we sort them depending on like their spectral similarity. Right? And then if they're similar, we connect them to each other and display them as molecular networks in molecular networks as such nodes. Right? And then yeah, like we define the similarity by, we can use different metrics. So in our case here, it's like a modified cosine similarity that kind of like gives us a score of like, yeah, just how similar these spectra are. And then again, like we display them as nodes in such networks. Now, I don't know, what level of annotation would that be? Also probably, yeah, exactly, 3. A little bit lower up, but yet, you know, this is really useful to systematically mine your data and like bring things to your attention, which you would not be able to like capture yourself, because yeah, with like this DDA and like this fast scanning experiments or like instruments, we get like thousands of MSMS per run, right? So like you can simply not go through them anymore. And yeah, like, okay, so now we can like organize this in networks and then propagate annotation within like this networks. And that's simply the thing that if one of them, you know, with the green check mark had like a library hit, so level 2 ID, then we can say, okay, the neighboring nodes, they're very similar, so they're very likely to be similar molecules. Then depending on like the chemical, you know, knowledge you have, and you look at the delta and that the fragmentation patterns, you may come up like with a structure, like I did for like the albicidins, right? That was before before I knew about molecular networking. Then when I learned about it and systematically then reanalyzed that non-targeted data I had, it was really interesting, because then like all like these other molecules would also appear, and I thought, oh wow, that's actually like even a bigger network, and there are way more analogs inside of that data than I thought. So yeah, I think this is really useful, and in the next couple of days we will show you how you get this from, well, our test data, but then hopefully also your own data. But okay, so now let's actually acquire some MSMS data. I'm remote connected here to the computer in the lab, and I can control the machine from here. I put already the samples in the auto sampler, and I put in the right column. So that's of course something I had to do during the lunch break before, and you may have to do, but like, yeah, most of the work still is like on the computer. And again, if some of you are interested, I'm happy to show you around how it looks there and how like the machine looks and where to change the column and so on. But I think most important for us is now the computer side, and basically like these 3 vendor software tools from Thermo. This is Tune, then Excalibur, and Qual Browser. And yeah, like Tune controls basically just like the mass spec itself. Then Excalibur controls, yeah, like the mass spec and coordinates it with like the LC. So we write our sequences in there and actually like acquire the data through like Excalibur. And then Qual Browser is the Thermo specific visualization tool where we can look at the data. I think they try to replace it now with Freestyle. So maybe if you recently bought an instrument, I don't know, Qual Browser might be still somewhere hidden, but they encourage everybody to use Freestyle. I like Qual Browser better, but I guess that's your choice. But yeah, so again, we want to set up a data-dependent acquisition method. And I'm going to reiterate on that because that's a really important take-home message for us. Data-dependent acquisition basically acquires MS spectra depending on like what MS1 masses are observed, right? And it cycles through like that duty cycles in which it does like one MS1 precursor scan. And then depending on what like peaks there are, it subjects those to the next MS events. And yeah, like, okay, we went a little bit into like data points and like chromatography and like representation of peak shapes. But yeah, like here, really like the speed and the number of data points is important if you want to do any sort of like MS1 feature finding and peak picking or like deconvolution or so. We can like talk about that in detail in a second again, if there are still questions. So yeah, we generate a lot of like MS. But yeah, how are we gonna set these settings up, right? So here, I want to now go through like every one of them because I think they're like really important. And unless you have already like super established MS methods in your lab that you can use from like the, I don't know, expert user there, you know, and you need to start from scratch. There's a lot of like room that you can do things not like ideal. So like understanding what those settings do, I think is really important. Try to go through quickly, but that's another important take-home message because everything we do tomorrow and the next days, you know, if you don't have like good data to begin with, it's going to be really hard to get good results at the end. So garbage in, garbage out, right? So, okay. So, okay, first thing, top N. So that is simply like the number of MS events per duty cycle. So that would be, I don't know, like a top 3 scan. So it would do like an MS1 precursor scan, and then would pick like the 3 most abundant peaks. And then in the next round, if they're going to be set on the exclusion list, then it would go down the ladder and like would pick the next 3 ones, right? Now, you know, would move on, so on and so on. So now you can like change the setting to like do only a top 1 scan. So then it's 1 precursor scan, 1 MS. Or you can do a top 50 scan. So then it does 1 precursor scan and 50 MS. So now, unless you have an ultra fast instrument like a timsTOF or so that can actually provide you with like fast enough speed, the odds are that you will end up like in that scenario and you do not get enough data point. And then, yeah, like you don't even reach the 5 data points I mentioned before, but you cannot represent any peaks on MS1 level. And even worse, right? Like if you wait too long between like the last MS to be triggered to like the precursor scan and you have really sharp peaks, then the odds are that like that molecule you observe during your precursor scan is already gone, right? So like there needs to be a somewhat like reasonable number of top N. So this is really important. That's why I put it like first here. Then monoisotopic precursor selection, that was your question, right? So here we can set basically the machine to exclude everything in an isotopic pattern, so we don't get like multiple MS of like the different like isotope groups. Okay, then very important, we have not mentioned that, isolation width. So this is simply like the window size, you know, of like the MZ range to be like isolated, and that can be, I don't know, 1 MZ. That would, I would say, is default, but it can also be like 10 MZ, right? And you make that window really wide open, and that now depends a lot on sensitivity, you know, because like typically there's like also some sort of like Gaussian distribution of like isolation efficiency and transfer efficiency, and that depends a lot on the instrument you use. And there, I think like Bruker may have made like a really cool TOF instrument, but at least like the Maxes we had available in San Diego did not have a very good quadrupole filter. So by default, you would just need to use that with like, I don't know, 5 or even like higher like isolation width in order to get enough like ions in for like an MS experiment. So I don't know if they fixed it in the meantime, but that was certainly something you had to know, because I'm used to like 0.5 MZ isolation width for like the QXF or 1 MZ. But if you use that on our old like Maxes, then you probably would have gotten like really low signal to noise for your MSMs. So yeah, here this needs to be optimized. If you work with like halogenated compounds and you want to maintain the isotope pattern throughout your MSMS to know at what location that halogen might be located, you may also want to like increase like that isolation width, right? Because otherwise, if you only isolate this here very small, right, only like the monoisotopic, then you don't get like the isotope pattern throughout your MSMS. Now, if you do like more like classical things, then like you typically don't care about the isotopologues and you actually want to have only the monoisotopic one. That's also what the setting before was. Then yeah, like isotopic exclusion. So here again, what I said, we want to exclude these peaks here, right, and only get like the monoisotopic one. Here, these settings, isotopic exclusion and monoisotopic precursor selection kind of like go a little bit hand in hand. Okay. So monoisotopic exclusion precursor selection is that it triggers MSMS really on the monoisotopic one. And the exclusion is just that after this one is triggered, the next ones are excluded. Yeah, you can use one without the other. Maybe if you look for like, you know, again, halogenated compounds, so they become like more important. Classic metabolite, you would have a isotope pattern like this, you know, then you don't really need monoisotopic precursor selection. So then it's optional. It's more like for certain compound classes or for larger molecules like peptides or proteins. I don't know. Like the one we have, you can select that. I don't know about waters. So I think most instruments you would do proteomics with, they probably have a setting like that. Okay, then again, very important dynamic exclusion. This you can turn on or off, right? So it basically avoids MSMS to be triggered over and over from like the same molecule. And now if you have a big peak here, like this one, right, and you have like very short duty cycle times, you know, that you would get multiple duty cycles over that peak, you know, then obviously you would get multiple MSMS triggered in each of those duty cycles, which may not be needed, right? You only need ideally, well, let's say 2, but 1 is already fine, right? Ideally, that should be at the top. That we get to at the next one, but like, yeah, like over and over triggering of like the same MSMS is like wasting basically scans. And this becomes like very bad when you have like one massive feature that is a peak from the beginning to the end of your chromatogram, and you waste, I don't know, like 20% of your MSMS events just on that, because in every duty cycle, it's triggered. So their dynamic exclusion prevents that. It's typically, there are kind of like different settings inside of that dynamic exclusion thing. That's kind of like the duration for how long you want to maintain like a ion in that exclusion list, right? That's also, I think with the QExactive, it's really like very simple. There's not much you can do, but with like older instruments, you can also like set like a repeat count. So that's like the number, how many times you want it to be triggered before it actually be put on like the exclusion list. So yeah, this like depends on like the instrument platform. Okay, then apex trigger. So this is exactly what I just showed here. So if you have a chromatographic peak, you know, you want the MSMS event ideally to be triggered at the top. But what happens if this is a really big peak? Typically it's triggered as soon as like the level here comes up a certain value, right? So then you get like an MSMS here. Now, if you have very stringent like dynamic exclusion settings, it's going to be put on the exclusion list and not triggered at all. So like it would be good if the machine would actually wait till that peak is on the top and then trigger the MSMS. So this is a very nice setting on the QExactive platform, and I think on the newer thermo instruments that you have the so-called apex trigger. It's basically you can like set like a time range at which like this apex needs to be otherwise it triggers the scan. So there's a little fine tuning needed, but yeah, in my experience, it's been worth it. Okay, then yeah, resolution. Depending on the machine, you can like set that like easily or not. So again, with like the FT based instruments, you can like change this by changing the transient time, and that also dramatically influences the number of data points again, you know, because yeah, higher resolution just takes like long. And then if you go to like unreasonable levels, then you may have not enough data points to like detect peaks. So here really it's important to like calculate that, right? So like then you say, okay, like at this resolution, it scans at that speed plus like my my fill time for like the C trap. You know, what would I end up with like at the maximum HEC fill time? And then yeah, go from there. And then yeah, depending on the chromatography you use, have it like appropriate. Okay, then micro scans. That is a very interesting setting. It's a little bit advanced. Default on the Orbitrap would be just 1. But on QTOFs, it's like, it's a different story because they're like the number of like scans that you accumulate will dramatically like change like signal to noise. I can't tell you what the default on the different platforms there are. Maybe Steffen in the back can. How many scans do you accumulate on the timsTOF? Okay, well.
And they accumulate for like 1 centimeter. That depends on like the width of the kilogram each.
So it's way more. So it scans at way higher speeds. But if you would like not accumulate them and get only like single scans, it would be very noisy, right? So there it's really important to set that appropriate. Also, I know from Hannes Link's lab, with whom we are sharing our mass spec lab. So they have an Agilent QTOF, and yeah, that's a central setting, like the number of accumulation of scans. For us on the Orbitrap, again, like for metabolomics, we use typically 1 microscan as default. If we use top-down, if we use it for top-down proteomics stuff, then I increase like the number of microscans in order to get like more better signal to noise. So this is really a central setting there. And obviously, like every like double it, then it also doubles the time it takes for like 1 scan, right? So like you cut like your scan speed in half, or I don't know, 10-fold if you would increase it to 10. Okay, then normalized collision energy. So this is the energy you activate your ions with in the collision cell. So normalized because it's like set relative to like the size or like the mass of an ion, right? So that's a typical thing we use on the Q-exactive. Other platforms you may do not have normalized collision energy. There you have like collision energy, and it's like given in a kind of like absolute value. So for us here, it's obviously it's relative in percent. There is an important thing. We can use stepped collision energy, so that actually activates things like at different energies, which I particularly like because you never know what's like the ideal collision energy. And if you do that step thing, you kind of like hit it a little bit with everything and typically get like a little bit like richer spectra. Again, that depends on like the instrument you have. Some can do that, stepped collision energy, others can't. So yeah. You need to figure that out what's best. Often libraries are also acquired just that like by default at different collision energies. So I think NIST, for example, has a lot of like different like
Yeah, I fully agree. One drawback on the step is that all the data is merged into one spectrum.
Yeah.
It would have been good. 3 files.
Yeah. I agree. The trade-off is again speed, right? If I get like 3 single MS events at 3 collision energies, I need to use 3 scans. If I do it stepped, you know, then it's only 1 scan. So I have like 3 times more MS. Now, if I have a very simple sample, or if I have a, let's say, a natural product, I isolate it and I want to like find out a lot about the structure, then I would for sure run it at separate, like different collision energies, but I have like the time to spare, right? Not in a non-targeted experiment of like thousands of different compounds. And then, yeah, last but not least, AGC. I guess we talked a lot about that. Remember the Three Stooges syndrome of the Simpsons. Yeah, like you need to set that appropriate, that you don't have space charge effects, and that you have an appropriate dynamic range. If you're not so sure about it, then typically leaving it at default is kind of like a good idea. Better to put it to like crazy low or crazy high values. All right, so now how does that look on the instrument? So yeah, I'm connected here to like the Q-exactive in the lab. And what you can see here is the tune. So this is basically just the control interface of the mass spec, and you can see here, okay, it's scanning. So I get like some scans here. At the moment, it's just like MS1 because I'm not like running any samples. So it's kind of like just like idling. I may also find it in standby. That's the default by what we leave it. So you won't see any scans if I try to standby here. But because I was showing somebody something, I had to turn it on. But yeah, typically I would like find it like that, and then I turn it on here. And then, yeah, as a very first thing, I want to see that something is moving in there, so I actually see scans, right? If I don't see anything here, it's weird. Because it's so sensitive, it always detects like some ions, right? So that's kind of like sanity check. Then here, like the traffic light tells me about like hardware status and like like instrument performance, things like calibration. If I haven't calibrated it recently, then typically that light is yellow. And it tells me, hey, you have to do like a calibration. So make sure it's calibrated, also in the appropriate mode, right? So you typically calibrate for both positive and negative mode. So now we're going to run some positive mode samples, and like I need to have it calibrated. Fortunately, we just did it yesterday or so. Okay, so yeah, that looks good. So I'm already done with the tune then. I just minimize this. And then I go to the, oh no. Okay, that's bad. Because that means that something is leaking, and I now actually have to go to the lab and fix it. But I think it doesn't matter for us. Let's just go to the other tool and let me explain what we're gonna do here. Okay, so we have our sequence, and that is basically a little bit what Martin showed you earlier, just that I did it with like my very own taste of things, right? So we don't have a pooled QC here. We run MS on all the samples. I have like this QC runs before and like after or like before and in between like the samples, and then yeah, like my different samples here are ran. Now, a good question is, how do I generate this like sample list, especially if it's long? So fortunately, you can like import and export those lists as CSV. So what I actually have on this computer here is like I generated the sample lists before here in Excel, just like with here a template, and juggling like names and randomizing things in Excel is like a little bit easier than in the software. And then I just saved this as CSV file. And then here, when I go back to the mass spec, I can actually import this sequence as a CSV file. So this was from Federico, but like now today, our sequence would be here in my folder, right? And then sister summer school. There we go. So I can import this, and yeah, now again, you would see the same sequence. And yeah, basically what this tells you is, okay, there's the sample names, there's a file path, a sample ID, which is not, you don't need to have that. And then there's very important the instrument method, to position in the autosampler, and then the injection module. Yeah, what I want to do is I want to like briefly walk you through like this method here, and then basically go back to the different settings I just explained, because you will find them all in like this method editor. So that's how it looks. We have here two symbols on the left. It's like the LC and then the mass spec here. And then here, when I click on the LC, I can like change like different settings for the gradient. So here we, use like a two-step linear gradient, acetonitrile water for reversed phase column. We have like here a 2.5-minute washout phase at 99% acetonitrile at the end, and then also 2.5 minutes re-equilibration to basically bring the system back to our initial condition. Okay, that's pretty straightforward. Not so much a change, but as soon as I go here, like now to mass spec, then here on the right, you can see that there is actually a lot of different parameters, right? And now when I go up here to advanced, I can even see a couple of more. And then, yeah, so it starts with like simple things like the runtime. So that would be just like the matching time to the chromatography. Then the polarity. So here I decide do I want to run positive mode or negative mode. Then here default charge stage. That is important for like the collision energy calculations. Now in metabolomics here, I would assume most of them are 1. So by default, this is 1. And then what Taido mentioned, I can add an exclusion list. Like, yeah, I just don't exclude anything for now. So this is just not selected. And then, yeah, like sort of from the settings I showed you, and you can open this up in the PDF I shared with all of you if you want to reiterate on them. Yeah, there's like micro scans, right? So this would be 1. Then now here for full MS, so this means MS1, resolution will be 120,000. So it's relatively high resolution. Then my HEC target for MS1 will be 1E6. And then like this maximum injection time, so the time the bouncer waits till like the ride is full, before they send it out for the scan, would be 100 milliseconds. And also there, that needs to be like somewhat like reasonable, like so in that time, ideally we should like reach that HEC target. Okay, and then like yeah, number of scans, so I can like do also multiple scans per duty cycle. By default, this is also 1. And then very important, mass range, right? So depending on what kind of molecules you're looking at, you want to change this. For like, yeah, standard metabolomics, we typically scan from 150 to 1,500. There is only a certain ratio between like the biggest and the smallest mass that you can like do in the same experiment. That is not a case with TOFs, but for like Eintrap instruments, yeah, like I would set this here to now 50, then it would automatically change the highest mass C to like a lower value because it can only scan for like a certain ratio between the two. I set this to 300, then I can easily scan here to, I don't know, 5,000 or so. But yeah, so this really, 4,500. Let's go to 400 and then we can probably just. All right, then I can decide whether to acquire in profile mode or centroid. So who of you does not know what the difference between profile and centroid is? Okay, yeah, this is an important thing. So if we look at the mass spectrum, again, like we have peaks here, right? So like ideally some type of like Gaussian peaks. So that could be a mass spectrum, with like an isotope pattern. And now obviously, depending on the resolution, we have like many data points here, right? So much more than in the chromatogram because yeah, it's way higher resolution. But it also means that it's a lot of data, right? And we can simply kind of like remove all these data points and only look at that one data point at the top, and then draw this as a line. And then instead of, I don't know, 1,000 data points, we have now only 3 of like this particular peak. And that is called centroid. And that is an important step we do in our data analysis tomorrow with MS Convert, or like Efi showed it earlier with the raw file parser, right? So that she used for like the centroiding. Now I can also do that directly on the machine and not like acquire things in profile mode. And if I do like really high throughput and like file size is an issue, it might be beneficial to like directly like acquire it in centroid mode. So it only saves, you know, like here, the top points and not the full thing. Now, as a mass spectrometrist, I like to see these Gaussian shapes because, you know, maybe there's like a little shoulder in here that the centroiding might miss, and I can go back to like the full profile data. But yeah, depending on the application, you might don't need that. Okay, then for MS2, we have the same type of settings, just like now I choose them differently. Again, microscans is 1 by default here, but now my resolution is much lower. This is because I want to get many MS2 and I just don't want to wait so long to get one MS2 at 120,000. So that's why I choose here the lowest one, 15,000, right? So here you could simply also select 120 or like even 240. Anyway, yeah, I want to have many, so I choose 15. And then also my HEC target I put lower because I expect less of a dynamic range within the MS spectrum than within like my MS1 full scans. And accordingly, I also like decrease the maximum injection time. Okay. So now, very important, loop count. This basically defines top N for my DDA experiment. So if I change this here to 20, then it means that it will make 20 MS scans per duty cycle. So it would quadruple almost the duty cycle time, right? Again, number of data points per feature that's perhaps like a critical setting next to like resolution. So here this should be appropriate to like the chromatography I use. For the UHPLC methods we try to keep it like under 1 second. And then with like 5 MS per duty cycle, we kind of like are in a good range. Then yeah, like here isolation width, what I explained before. By default, 1 MZ. Again, if I would look at proteins or like halogenated compounds or so, I probably would increase that. If I know that I look at halogenated things, I also use an offset because like the isolation width is just like a window. But if I'm only like interested in the more heavy isotopes, I can move the entire thing towards like the higher MZ. Then with increased window size, I would also use here such like an offset. Okay, then first fixed mass. This is optional for like the MS scan. You can simply say, okay, scan from always 50 upwards. I don't like to select it because then it changes it dynamically. And then if I have small molecules and big molecules, sometimes, yeah, you want to get like that really low MZ fragments, but for bigger molecules, you also want to get the big MZ fragments. So I leave that like unselected. Then, as I mentioned before here, collision energy. So we use NCE, so that's normalized collision energy. And then I typically use like this stepped collision energy here. And that's for basically most of our metabolomics runs. So unless I have a very particular compound I'm looking for, and I try to get like a really nice looking fragmentation pattern for like de novo structure elucidation, I just use that by default. That way I make sure that like my data remains comparable within data sets, right? Because then I just throw in, I don't know, samples from 5 years ago from San Diego to like stuff I run now, and it's the same collision energy settings. And then I assume that they, should cluster still together because they should result in the same patterns. No. It's just like it divides basically the activation time, which was HCD is really fast in like 3 different like zones at different energies. Okay, then also really important here, DD settings. So this is the data dependent settings. Here I can like put thresholds of like a minimum agency. So let's say I don't reach like the full AGC and it's below this value, then it does not even submit the ions to a scan, but just like cleans it out and goes for the next one. That saves me low quality MS spectra. And I think that is another thing we often see, particularly with also QTOF instruments, that a lot of MS spectra are just like noise, right? And then you waste scan time for them and they're not useful. So here, setting like appropriate thresholds, I think is important. yeah, you can do that based on HEC or like also like a relative intensity threshold. I think you select either one or the other. That's why I don't know if yeah, I can't select this right now. So yeah, it's based on HEC. Okay, then apex trigger. So here I say yes, use it, and the apex should be expected between 2 and 15 seconds. So if after 15 seconds there has been no apex detected, then it triggers it anyway. So that depends a little bit on the type of chromatography I use. 2 seconds means that at the beginning that it should at least take 2 seconds till it reached the apex before like the first occurrence. Yeah. Then for charge state exclusion, I only exclude here unassigned charge stages. But yes, I mentioned before, I could probably also, you know, exclude like the highly charged stuff because I don't expect any proteins in here. So I don't know, something like that. Single, double, and triple, I may expect some metabolites to be multiple charged. It's very rare that they're actually there, so it's not too critical. Okay, then peptide matching. So this kind of like also infects like the isotope pattern, and then preferentially triggers MS2 for things that are considered peptides. So this is a setting particular useful for proteomics, not for us. And then yeah, like exclude isotopes. We can either, you know, select it or not. And then dynamic exclusion. So this is really super simple. It just says, okay, if you seen something, wait at least 5 seconds before you trigger it again. This is very short for like exclusion time, but I like to have a little bit of redundancy. So if I would be, you know, more greedy, and I would say, yeah, give me more MS rather, than I would increase that. If I want to have like higher quality data and more redundancy, then I would decrease that. But yeah, so I think this is pretty much like the setup here for like my DDA method. You can see here on the other side, there's all sorts of like different experiments I could select. I could also add scan events for only like a full MS, you know, or I could do AIF, so that would be all ion fragmentation. That would be like for a DIA method. And I can build up, I don't know, even more complex things, but I think for today, let's focus only on like the DDA method. And let's not change, save any changes. So I'm pretty happy with this method. And I don't know, I thought, Paolo, did you fix the leak? Okay, I mean, okay, for now, like the most important thing would be that I just, you know, select this. And then here I can select the entire sequence and then hit run sequence. And then it will ask me, okay, run the sequence, row 1 to 24. And then at the end, after the sequence is done, should the system remain on? So during the day, I would select that if I know afterwards I want to run some more samples. Or I can like say, put it in standby. So if now that's the last thing before the happy hour I'm gonna do, I want the machine to like stop by itself afterwards. Okay, one thing at the end here, I included also some wash methods. So these are still simply some like very fast gradients within one method that kind of like are supposed to clean the method and then leave it at the end at 99% acetonitrile, which for us is like the storage condition for like the HPLC column. And then yeah, like within that standby function, it would also reduce the flow rate to like a small flow rate. So we constantly let the pumps run, which I think is better for the seals and the check valves. So and then yeah, it just like reduces the flow from 0.5 milliliters to 0.05 mils, and yeah, puts the mass back into standby. So yeah, obviously I'm not going to start this because I have to fix the leak first. But then like once the leak is fixed, I will basically just hit start, and then we're ready to go. And hopefully tomorrow we will have a bunch of files we can then process with Enzymine. Cool. Okay, I guess we're just on time for some refreshments. Are there any questions before we move to that part?
The apex trigger, the time you set, you just look at peaks first, how
Yeah.
Second question was, I see you used different injection volumes for the QC.
Yeah. So to be honest, so we use two types of chromatography. We use like normal flow and microflow, and I don't want to like make QCs for both. So we have it like kind of like in a range that we can also use it for microflow, and that is better with like smaller injection volumes. Now it's pretty concentrated, so like at 2 microliters, I get like a good signal. But then for like the other samples, so this is actually a normal flow method. You can see at 500 microliters per minute. Then like default injection volume would be 5. I think in an ideal world, we would have the same injection volume. But, yeah, maybe I'm just an amateur. Yeah.
When you said, for example, the HC MS method, but also you have to set it in the tune method, do you know which of them it will take?
Yeah. So your method here and no, the settings here and your method overrule the tune method.
Okay.
So yeah, I think there was in the older versions you could only set it in the tune method. Also the micro scans and so, but now conveniently they have now brought it into like the Excalibur methods too.
Also, short question. In the washing phase of the chromatography, you also acquire the MS2 or you?
No.
No.
No, I can show you how.
100%.
Yeah, let me show you that method too. Yeah, that's only MS1, and yeah, like we basically just delete it afterwards. But what it does is I run like this fast gradients here, which I think like, you know, if you have like sticky stuff on the columns, running like a couple of like fast gradients like that help you to get stuff down faster. And then at the end, it has like this long phase at 99% acetonitrile, and that's really just to bring it completely to storage condition, and then it goes to standby. Yeah, and then on the MS side, I don't know what we have, but it's just the full MS. And
But you do that.
I mean, you have to. I think we could also run it without any MS acquisition, but I kind of want to see, you know, does like the contaminations like eventually go down. Yeah. Yeah, and then another important thing here on the pump actually, what I also like to do, I don't know if it's here, but at least for the system methods, we typically record the pressure of the binary pump. And yeah, in our case, we have a makeup pump, so we have also quaternary pump, but depending on which one we use, we have this. Let me, yeah, here. For this one, it should be selected. And that tells you a lot of your, you know, equilibration time and if your pump works well, because any pulsation you will immediately see. And we recently had problems with our check valves, and then like monitoring like the pressure, it's perfect to take a look at it. Yeah, so again, here it's check C pump binary pressure. And it's really nice if I, show you the actually sample I just acquired earlier before it leaked. Let's see. So I run already a couple of QC mixes. And then, you know, you will see here this curve. Okay, that was, I think, the wrong method. But on this one here, yeah. You see we go nicely up like to like 550, then we turn the valve, the divert valve, so then it goes all the way to the ESI, and then we see a jump in pressure because now the ESI capillary adds pressure to the system. Then I see like this little curve, right? So like pressure increases. This is because we increase acetonitrile, and acetonitrile water has the maximum viscosity at 30%. So then once we hit 30%, you know, it goes back down. And then like it goes to like really high acetonitrile concentrations. and then like viscosity goes really like drops and pressure drops before we then, you know, at the here after the re-equilibration phase, come back up, and then we see it should, you know, get like flat. So now if any of these phases is too short, then I will see this in like the pressure profile, right? So I recently saw a photo on Twitter from somebody who had only like half a minute re-equilibration time in his method, and he was sharing a screenshot, and I thought, oh, how does that work? How do we get like starting conditions? And that is really important, because if you do not have that, then on your next injections, well, everything will like run through like immediately, right? You get really bad chromatography. So here, yeah, like looking at pressure is good. And then, yeah, I can show you how, do you see like this little things here? Like this little dips on the pressure profile? That's not good. I mean, I think it's within an acceptable range, but yeah, I called already the technician a while ago and said, hey, like that has like some problems with either check valves or like the seals. And I see this nicely in this pressure profiles. So yeah, if you don't monitor that, just put it in, you know, like the machine just like records it for you. Oh yeah, we use pre-columns, but also.
I read in one paper that pre-columns are not.
Yeah, might be not. Oh really? Okay, interesting. I don't know. Like, so I mean, we simply do it for economic reasons, right? Because like changing the full columns, like, so we use phenomenics, like kinetics, and they're like, I don't know, like $800 per column, right? And now, if, well, we have very diverse samples in the lab from like all sorts of things, and sometimes people just bring something that has a lot of PEG or whatever, and then you like ruin your column, and then it's better if you ruin only your pre-column. And then that one, yeah, it has a cartridge holder and you can exchange it. So yeah, basically most of the comps we have pre-columns.
For that reason, do you run any pre-screen studies before you run a full study? If there's contamination.
Yeah. If people like contact you before they have all the samples, then yes. But sometimes it's just, oh, Daniel, I have like this 200 samples. Can we analyze them? So, oh, okay. But then it's good if they either bring their own column or if there's a pre-column. But yeah, if I'm like, ideally one is involved in the planning, right? And then ideally it's not only me, but also a statistician who may does like some power calculation. But I think that's unfortunately not the norm. It's a more rare situation. Mm-hmm.
So, you know, more products, I guess. And you said that in our experience, high nitrogen concentrations of the elements are bad for the advantage over 95%.
Interesting. Yeah, I don't think we can avoid going to 99% acetonitrile. So that's.
I was wondering why I'm thinking of 100 for the wash.
Oh, like it's like we always like both pumps to run a little bit, right? So I don't like one because we have a binary pump, so it's a high pressure gradient system. And then if like, so one plug pumps only water, the other one pumps only acetonitrile. If I would go to 100, and one would stop. So it's, yeah, it's a common thing that you always maintain them at that low flow rate at least.
Should I ask you the question?
It's funny, like, so maybe you can text back if they do not use acetonitrile then. Because
she says that we don't go higher than 95%.
okay,
So they use, but
not okay, interesting.
Oh, she's also answering. Maybe try to change the composition of your element. That's what we do in order to have both pumps running. I guess.
Yeah. Okay, so 95 is better than 99.
Like 5% to nitrogen A and 95 to B. I like to switch them. Okay. Or I don't know.
Interesting. And they have a language too. I'm gonna look up the chat. Maybe I'll write her offline. But that's interesting.
And then Yen asked before, could you explain the tune setting? I guess
Yeah.
this is the best explanation.
Yeah, so there's not too much to change anymore. So on the QEHF, they actually completely eliminated here the tune parameter where you could specify certain like voltages for your analyte. So they just have a one fits all setting. I think you need the technician's dongle to actually unlock that setting now, which is an interesting, yeah, so I don't know, QExactive users here, there's no tune anymore. And then like the main thing that we change are like the ESI parameters, right? So that needs to be appropriate for like the flow rates you use. So sheet gas, auxiliary gas, sweep gas, then the spray voltage, and then the temperatures, right? And then the main setting, that's what I was asking for earlier, is like this S-lens RF. So that has a huge influence in kind of like what mass ranges it favors. So like that we change depending on what type of like molecular weights we're looking for. So yeah, default is here 50 for us, but if I would look at like proteins, I would increase that. Yeah, so it's really what Stefan said, or like what Robin said. It's kind of like limited what you can do here. It might look very different on the LTQ Orbitrap. So there you could like select like a lot of like different voltages, and for sure it's very different on the Bruker platforms. Cool. All right. I guess if there's no more questions, then hopefully there's some. Oh, Stefan?
Just RF looks like in like a rough guideline, higher RFs for higher masses, or
Yes, in our experience, yes. Yeah. Cool. All right. Thanks again. And yeah, let's have some drinks.